SwayamPrabha. Digital India. Educated India.
Welcome to this tutorial. Today we will go through a few examples based on gas power cycles such as Otto, diesel and Brayton. So let's start with the first question. The compression ratio of an air standard Otto cycle is 9.5. Prior to the isentropic compression process, the air is at 100 kilopascal, 35 degree centigrade and 600 centimeter cube. The temperature at the end of the isentropic expansion is 800 Kelvin. Using specific heat values at room temperature, determine the highest temperature and pressure in the cycle, the amount of heat transfer in kilojoule and the thermal efficiency. So, if you see the whole process on a PV diagram, since it is an Otto cycle, so the first process will be isentropic compression from state 1 to 2, followed by heat addition at constant volume from the state 2 to 3, and then isentropic expansion from state 3 to 4 and heat rejection at constant volume. Okay, and heat will be coming here in. Okay, so this is the complete Otto cycle. Now we have to find the highest temperature and pressure in the cycle, which will be corresponds to this state, which is state 3. Okay, so starting from the process 1 to 2, since it is an isentropic compression, so T2 V2 to the power k minus 1 equal to T1 V1 to the power k minus 1. So from here we get T2 equal to T1 times V1 upon V2 to the power k minus 1. Okay, T1 we know it is given in the question, which is 35 degree centigrade. So after putting this value here, 308 Kelvin, V1 by V2, which is compression ratio, is given to us, which is 9.5. So 9.5 and k minus 1, since k is 1.4, so it will be 0.4. So from here we get T2 equal to 757.9 Kelvin. Okay, now here we assume air as an ideal gas. So from ideal gas equation of state, P2 V2 upon T2 will be equal to P1 V1 upon T1. Okay, so from here we get P2 equal to V1 by V2 times T2 upon T1 times P1. Okay, so after plugging these values, we get P2 equal to 9.5 times 757.9 divided by 308 Kelvin into initial pressure, which is 100 kilopascal. So this gives us pressure at the state 2, which is 2338 kilopascal. From the process three to 4, which is an isentropic expansion, so T3 will be T4 times V4 upon V3 to the power k minus 1. We know T4, which is 800 Kelvin given in the question. Compression ratio is 9.5 to the power 0.4. So, from here we get temperature of state 3 is 1969 Kelvin. Okay. Now, from the process from the process 2 to 3, which is constant volume heat addition. So, from the ideal gas equation, P3 V3 upon T3 will be equal to P2 V2 upon T2. Okay. Since volume is same, so from here P3 will be T3 upon T2 times P2. Okay. So, P3 will be 1969 upon 757.9 Kelvin times 2338 kilopascal. So, P3 will be equal to 6072 kilopascal. Now, we are asked to calculate the heat coming into this cycle. Okay. So, heat is given during the isochoric process from the state 2 to 3. Okay. So, Q in will be equal to mass times change in internal energy, okay, because delta V is 0. Since it is air is behaving as an ideal gas, so mCV T3 minus T2, it will be reduced in this form. Now, we need to know m. CV we can get it from the air properties table, T3 and T2 we know already. Now, from the ideal gas equation we can get m equal to P1 V1 upon RT1. Okay. So, after plugging values of these variables, 100 kilopascal P1, volume is given in the question. So, it is 6 into 10 to power minus 4 meter cube divided by 0.287 kilopascal meter cube on kg into Kelvin, and temperature T1, which is 308 Kelvin. So, after solving it we get m equal to 6.788 into 10 to the power minus 4 kg. Okay. So, now after plugging these values we get Q in equal to 6.788 into 10 to the power minus 4 into 0.718 into change in temperature 1969 minus 757.9 kilojoule. So, after solving it we get 0.59 kilojoule heat is coming into the cycle. Now, we need to know thermal efficiency. For that we need to know heat coming out of the cycle. Okay. So, Q out will be equal to mCV T4 minus T1. Okay. We know m, we know CV, and we know T4 and T1. So, after plugging these values here we get 0.24 kilojoule. Okay. And W net will be, W net out will be equal to Q Q in minus Q out. So this gives 0.35 kilojoule. So now thermal efficiency would be W net out divided by total heat going into the cycle. So from here we get 0.35 upon 0.59. So this gives 59.4%. So this is the thermal efficiency of the Otto cycle. So moving to the next question. An ideal diesel engine has compression ratio of 20 and uses air as the working fluid. The state of air at the beginning of the compression process is 95 kilopascal and 20 degrees centigrade. If the maximum temperature in the cycle is not exceed 2200 Kelvin, determine the thermal efficiency and the mean effective pressure. Assume constant specific heats for air at room temperature. So this is an ideal diesel engine. So if we see the cycle on a PV diagram, so the first process will be isentropic compression from the state 1 to state 2. Then heat is added in this cycle at constant pressure. Okay, so heat will be going in at constant pressure. Now from the state 3 it will expand isentropically to the state 4, and finally it will rejects heat at constant volume. Okay. So this is the complete diesel cycle. Now we are asked to calculate thermal efficiency and mean effective pressure. So what is thermal efficiency? Thermal efficiency is at a W total work coming out of the cycle divided by total heat going into the cycle. From the process 1 to 2, which is an isentropic compression. So temperature at the state 2 can be obtained using temperature and volume data given at state 1. So V1 upon V2 to the power k minus 1. Okay, so T1 is given 293 Kelvin. Compression ratio is given to us, which is 20 to the power 0.4. Okay, since k is 1.4. So this gives T2 equal to 971.1 Kelvin. Okay, now from the process 2 to 3, which is an isobaric process, so from that V3 upon V2 equal to T3 upon T2. Okay, since P2 equal to P3, and we have assumed that air is behaving as an ideal gas. So this ratio V3 upon V2 will be equal to 971.1 Kelvin. So this gives 2.265. Okay. So now from here we can get V3 in terms of V2, which is 265 into V2. We will make use of this in the next process. So now at constant pressure, heat is going into the cycle, which is Q in equal to change in enthalpy, right, S3 minus S2, which will be equal to, since this is constant pressure process, so this will be equal to Cp times T3 minus T2. Okay, and we know Cp from the air properties table kilojoule upon kg into Kelvin times temperature difference T3 minus T1, which is 971.1 Kelvin. So from here we get Q in per kg, which is 21235 kilojoule per kg. Okay. Now heat is rejected at constant volume. So Q out equal to U4, since it is heat is being rejected from the process 4 to 1. Okay. So Q out will be U4 minus U1, okay, which will be equal to CV T4 minus T1. Okay. So from the properties table we can get CV value, which is 0.718 kilojoule per kg Kelvin, change in temperature, which is 920.6 minus 293 Kelvin. Okay. So after solving it, we get Q out equal to 450.6 kilojoule per kg. Okay. So since we know Q in, Q out, we can calculate net work coming out of the cycle equal to Q in minus Q out, which is equal to 784.4 kilojoule per kg. Okay. So since we know W net out, now we can calculate thermal efficiency of the cycle, which is 784.4 upon 1235. Okay. So now from here we get 63.5%. Now moving to the second part of the question, where we are asked to calculate mean effective pressure. So mean effective pressure will be equal to total net work coming out of the cycle divided by the volume 1 minus 1 upon R. Okay. So since we don't know initial volume, but using ideal gas equation of state, we can get P1 equal to R T1 P1, which will be equal to 0.287 kilopascal meter cube on kg into Kelvin times temperature, initial temperature, and P1 is 95 kilopascal. So from here we get V1 equal to 0.885 meter cube per kg. So after plugging this, MEP will be equal to 784.4 kilojoule per kg upon 0.885 meter cube per kg times 1 minus 1 by 20. So this gives mean effective pressure equal to 933 kilo Pascal. Okay. So now moving to the next question. A simple Brayton cycle using air as the working fluid has a pressure ratio of 10. The minimum and maximum temperature in the cycle are 295 and 1240 Kelvin. Assuming an isentropic efficiency of 83% for the compressor and 87% for the turbine, determine the air temperature at the turbine exit, net work output, and thermal efficiency. Now since this is a Brayton cycle, so if we see this process on a TS diagram, okay, the first process will be an isentropic compression from the state 1 to 2, then heat addition will take place at constant pressure, then isentropic expansion will take place in the turbine and heat rejection will also take place at constant pressure. So 1, 2, 3, and this process will be 4s. Since this is an ideal process, so 1 to 2 years, but actual process will follow the path 1 to 2, and same here in the turbine as well, it will follow the path 3 to 4 because of irreversibility of the system. So, it is given that minimum temperature is 295, which is corresponds to this state 1. So, T1 equal to 295 Kelvin. Okay. It has already given that maximum temperature is 1240 Kelvin, which will be corresponds to this state 3. Since we are asked to calculate thermal efficiency and turbine exit temperature, which is T4, we need to know temperature at all these states. So, starting from the first state, T1 equal to 295 Kelvin. So, from the table A17 corresponds to this temperature, we can get enthalpy equal to 295.17 kilojoule per kg. Corresponding reduced pressure will be 1.3068. Okay. Now, to get enthalpy at 2s, P reduced at the second state will be P2 upon P1 times PR1. Now, since the compression ratio is given equal to 10, so 10 times 1.3068, which gives 13.07. Okay. Now, corresponding to this reduced pressure, okay, we can get corresponding enthalpy equal to 570.26 kilojoule per kg from the table A17, and T2s as well, which is 564.9 Kelvin. Okay. Now, from the compressor efficiency, which is equal to isentropic work to the actual work, ratio of isentropic work to the actual work will be equal to H2S, change in enthalpy, H2S minus H1 upon H2 minus H1. Okay. So, from here, after solving it, we get H2 equal to H1 plus H2S minus H1 divided by compressor efficiency. So, compressor efficiency is given in the question. So, from here we get H2 equal to H1 already we have calculated, which is 295.17 plus 570.26 minus 295.17 upon 0.83. Okay. So, this gives 626.6 kilojoule per kg. It is given in the question that T3 equal to 1240 Kelvin. Okay. So, from the properties of air, we get H3 equal to 1324.93 kilojoule per kg, and PR3 equal to 272.3. Okay. So, using this we can get PR4 equal to P4 upon P3 times PR3, which is equal to 1 upon 10 times 272.3, which gives 27.23. Okay. So, correspond to this reduced pressure, H4S can be taken from the table, which is 702.07 kilojoule per kg, and T4S equal to 689.6 Kelvin. Okay. So, from the thermal efficiency of turbine, we can get S3 minus H4 equal to S3 minus H4S. Okay. So, from here, after rearranging, we get H4 equal to S3 minus thermal efficiency of turbine times H3 minus H4S. Okay. So, after plugging the values of these variables, we get H4 equal to 1324.93 minus 0.87. Thermal efficiency is given in the question, 1324.93 minus 702.07. Okay. So, this gives H4 equal to 783.04 kilojoule per kg, and corresponds to this H4 and PR4. T4 from the table A17 can be calculated as 764.4 Kelvin. Okay. So, in the second part of the question, it is asked that we have to calculate total work. So, Q in will be S3 minus S2, right. So, this will be 698.3 kilojoule per kg, and Q out will be equal to H4 minus H1 equal to 487.9 kilojoule per kg, right. So, W net will be Q in minus Q out. So, this will be equal to 210.4 kilojoule per kg. Now, thermal efficiency of the whole cycle will be W net out divided by heat going into the cycle. So, this will be equal to 0.3013, that means 30.1%. So, we will stop here. We will meet you in the next tutorial. Thank you.